Section 4.2, what derivatives tell us? We're going to cover increasing or decreasing functions, finding maxima and minima, and finding changes in concavity and inflection points. So, first is testing for increasing and decreasing. If the first derivative of your function is greater than 0, then f of x is increasing. If your first derivative is less than 0, then your function is decreasing. For example, if we have the function x squared, then our first derivative is equal to 2x. That means our first derivative is greater than 0 when x is greater than 0, and our first derivative is less than 0 when x is less than 0. And you can see that by looking at my nice little diagram there. Identifying maxima and minima. So maxima and minima are points on your function that have the smallest possible value of x, or smallest possible value of y, or the largest possible value of y. So to find the maxima and minima, you use the first derivative test. To find local maxima, if f prime changes from positive to negative, then you have a max at whatever point that is. And for local minima, it's when your first derivative, f prime, changes from negative to positive. For example, if we have the function 3x to the fourth minus 4x cubed minus 6x squared plus 12x, then our first derivative, after it's factored, is 12 times the quantity x plus 1 times the quantity x minus 1 squared. So, in looking at this, we see that the sign of our first derivative of f prime is negative to the left, or for x values less than our first critical point at negative 1. Then we see that between our critical points, negative 1 and 1, we see that the first derivative is greater than 0. And for any value greater than the critical point on the right, x equals 1, we see that the first derivative is again greater than 0. So what this means is for points left of negative 1, f of x is decreasing. For points between negative 1 and 1, where our first derivative is greater than 0, our function f of x is increasing. And again, to the right of our second critical point, our first derivative is again greater than 0, so our function f of x is increasing. Testing for concavity. So concavity is essentially the direction of the bowl shape of our function, so to say. So if we have an invisible bowl right here, then this area here is what's called concave up, and then correspondingly here, basically where the bowl is facing downwards, that's concave down. So in places with a corner or a cusp, like here, we see that we have concave down on the left, and we still have concave down on the right. For functions like x squared, the function is always concave up, and for functions such as negative x squared, we see that it's always concave down. So, if our function is differentiable, then if our first derivative is increasing, then our function is concave up. If our first derivative is decreasing, then our function f is concave down. Furthermore, if f changes concavity, meaning if f prime changes from increasing to decreasing or from decreasing to increasing, then we have what's called an inflection point. Testing for concavity. If the second derivative of our function is greater than 0, then we know that our function is concave up. If our second derivative is less than 0, then our function is concave down. If at some point c, some arbitrary point, our second derivative is equal to 0, then at that point c, there is what is called an inflection point. For example, if we have the function 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1, our first derivative is the same as in the previous example, and our second derivative is then 36x squared minus 24x minus 12, which, once it's factored, is 12 times the quantity x minus 1 times the quantity 3x plus 1. So where this second derivative is equal to 0, like I said, those are what are called inflection points. And in this example, we can see that our inflection points are at 1 and negative 1/3. So, to the left of the inflection point at negative 1/3, meaning for x values less than negative 1/3, our second derivative is positive, meaning it's concave up. Between our inflection points, if you plug in an arbitrary value between those 2 points, we see that the sign of our second derivative is negative and therefore concave down. For points to the right of our second inflection point, choose a random value, we see that the second derivative is positive and therefore concave up. So the second derivative test. The second derivative test tests for local extrema, meaning local minima or local maxima. So using the second derivative again, if the second derivative is greater than 0 at some point c, then f has a local minima at c, and if f double prime of c is less than 0, then it has a local max at c. And if our second derivative is equal to 0, then the test is inconclusive and you'll have to try something else. So that is an introduction to section 4.2, what derivatives tell us. If you have any questions, come see me at my help hours, Thursdays and Fridays from 2 to 6. Alright.